I'm recording right now. Oh, stop it. Okay. Here's assignment 3. What we're going to do, I want to review rotational kinetic energy with you and define from that rotational or moment of inertia, rotational inertia, angular mass. It's a way of thinking about it. Yesterday I forgot to mention that it has a variable called I. If you see capital I without a vector hat on it, that means it's rotational inertia, and or moment of inertia. We're going to cover 10.5, and we're going to figure out what the rotational inertia is for extended bodies. Guess what? There's calculus involved there. We're going to define it using an integral. We'll also talk about the parallel axis theorem. I'm not going to prove it. I'm just going to tell it to you. There is a nice little proof in the textbook, though. So if you need to have everything proved, read the book. And then we're going to talk about torque and angular acceleration. And you're going to see how torque is kind of the angular analog of force. So let's get started. Here's what we did. We took imagine you've got a mass on a string. So this is our little review here. If we have a mass on a string, okay, and it's rotating, you know, it's going through circular motion, okay, well, it has kinetic energy, and let's say it's rotating with a certain angular velocity omega, and we're going to keep this in radians per second. Well, we said that, you know, kinetic energy is just equal to 1/2 mv squared. Well, but we can relate the velocity of this, the linear velocity v, or the speed I should say, to the angular velocity. We said that v is equal to r omega. So we just substitute this in here, and so we can express the kinetic energy of our object moving in circular motion here as 1/2 m r squared omega squared. Now we kind of group this together here, okay, and we say, okay, the mass of this object times the radius, now this is r, right, from here out to here. We kind of group it together. Now, what if I had a whole bunch of particles and they're all rotating with the same angular velocity, and that's key. They're all rotating with the same angular velocity. Maybe these are pennies or coins on a disk that's spinning. Okay, so I might have one over here, and I might have one with a different mass over here. I might have one, you know, a little closer right there, right there. And so they all have different R's. So we'll call this Ri, and this is Mi. So they all have different R's and different masses and so on. But I would just add up their kinetic energies, right? The kinetic energy is just the kinetic energy of this object, plus this object, plus this object, plus this object, and so on. As long as they all have the same angular velocity, all I have to do, look, omega is going to be the same for each one. So it's going to factor out of the sum. The 1/2 is the same. It's going to factor out of the sum. And all we have to do here to get the total kinetic energy is say it's 1/2 times the summation of mi ri squared, where I equals 1 to n times omega squared. Now, this right here is what we called, yesterday we called this rotational inertia. Moment of inertia, it's called that too. I like to think of it as angular mass. It's the angular motion equivalent of mass. Now it does have mass in it, doesn't it? But it also has how far that mass is away from the axis of rotation. Obviously, if something's really far away from the axis of rotation, it's going to be hard to make that thing spin at a certain angular velocity. You got to get up to a much higher speed, and therefore it's going to take more work to do that. So this is the angular equivalent of mass, and we have a variable name for it, I. Okay, And so we can say this, that the kinetic energy expressed in terms of rotational variables, okay, is 1/2 I omega squared. Now, these variables are analogous to our linear variables. This is, if we want to call this K sub r, the rotational kinetic energy. We can express it in terms of our linear variables. I'll call that K sub L. And where we say this is 1/2. Well, what's the linear equivalent of I? M. And what's the rotational equivalent of omega? I mean, the linear equivalent of omega. It's V. So this is really cool. This is just like what we did with the kinematic equations. You know, they're analogous variables. And this extends all the way into kinetic energy. Okay, any questions on that?
How do you go from W to V?
Well, this is angular velocity. This is linear velocity. I'm just saying the variables are analogous.
Oh,
okay.
Velocity if there was
right.
Rate.
Well, look, I mean, you look how we derived it anyway. We derived it by expressing our linear velocity out here, or at least our speed, in terms of r and omega. So, you know, you can just go backwards to get this equation. I'm just pointing out the analogous nature of the variables. Okay, so let's go on to 10.5. Okay, and in section 10.5, we talk about figuring out the rotational inertia for objects that have extended mass. Okay, so this is we're going to calculate I for extended bodies. Now that's not the title of the section, but it should be. So let's say I've got some kind of blobby shape, and I'll put my origin right here, and this thing is rotating. And always put your origin at the axis of rotation, okay, because it just makes everything easier. And all the problems we're going to be doing in this class, the axis is fixed. So anyway, it's a good place to put it. Well, now, you know, instead of a system of particles here, we've got a blobby shape. So we've got to divide it up into a lot of little tiny particles and then sum them all together. So we'll put a little tiny infinitesimal particle right here. It's got a certain distance r, and it's got a little mass of dm, little tiny chunk of mass. And so we have here our I. Well, what did we do with I before? We had a summation of mi, you know, ri squared, right? Well, now we're going to, instead of having a summation of a discrete number of particles, we're going to have an infinite number of particles, and we're going to sum them all up using the magic of integral calculus. We'll put the dm over here, and then this is just going to be r squared. And so this is, for extended bodies, this is our equation for rotational inertia. Now, if you've got an object that you can break up into a system of particles, use this one. But sometimes we have to use this, and therefore we can only really do this for highly symmetrical mass distributions. So like spheres and cylinders and hoops, maybe rods, things that are really well behaved that we can use mathematics to solve. You know, we can actually use the techniques from your calculus classes to solve this integral. So that's what we're going to do. We'll do a couple of them here. We'll do example 10.5. And this is on page 303. And basically, here's what you're given. You're given a hoop, like a hula hoop. Okay, so let's look down on it. Okay, so it's got, here's my hoop, and it's got a radius of r. We'll use capital R. And it's got a total mass of m. So if I put the hula hoop on a balance, figure out its mass, it's got a total mass of m. And so what I want to find is the rotational inertia, obviously, I. Well, let's solve it. So this is an extended body. So I've got to write down the integral. Start here. If you were taking the AP test, you just writing that down, you probably get a couple points. All right, so now you got to take this thing apart. Now, first thing I always try to do is pick a little dm. Where is my dm? Where's my little mass? So, oh, there it is. I'll choose that as my dm. Now, then think about all the other dm's that are going around here. How far away are these little dm's from my axis of rotation? They all have the same r. So in other words, this is going to be equal to the integral of r squared times all the little dm's. And so, since this is a constant, it comes out of the integral, doesn't it? Well, what does this mean? Sum all the little dm's. Well, if I sum all the little dm's, what do I get? I get the total mass. So this is the equation for I equals, for some reason we put mr squared instead of r squared m. Doesn't matter though. Now, here's what this means. If you have a hoop, I want you to think about this, and it's rotating about its center of mass, you know, in this plane like this. We're not flipping it like a coin. It's rotating like that. All of the mass of the hoop is as far away from the axis of rotation as you can get. So this is the maximum rotational inertia you can possibly get. A hoop has the maximum rotational inertia. Now you might think, well, wait a minute, doesn't this hoop have some thickness? Yeah, it does. In reality, it does. But what we have here is an ideal hoop. So the thickness of this is insignificant compared to the radius. And a hula hoop, this would work really well. If you had a hula hoop and you want to know the rotational inertia of the hula hoop, this would work really well for it. So you can model it like that. So if the thickness of this is really insignificant compared to r, you can use this to model it. Well, now let's talk about another shape. And so let's do example 10.6. So 10.6, example 10.6 on page 303. Well, let's see what we're given here. It says, calculate the moment of inertia of a uniform rigid rod of length L and mass M about an axis perpendicular to the rod passing through its center of mass. Now this one's a little more complicated. Here we have a rod of length L. The axis of rotation is through the center of mass. So that's where we're going to put our origin. So we'll make this the y-axis and this the x-axis. That's totally arbitrary. And it has a total length of L. And it has a total mass of M. And we want to find I. Well, let's solve it. Now this one you actually have to evaluate the integral. This is an extended body, so I know that I have to use the integral. And it's r squared dm. But unlike the hoop, the r is not a constant. That is, the distance my little dm is away from the axis of rotation varies. Pick a little dm. Here's one. But my little dm's vary from my distance from the axis of rotation. So therefore, I'm going to have to modify this. I've got to work it a little bit. First thing I want to do is change variables. I want to go from r to, well, how far away is my little dm? It's a certain distance position on the x-axis, so I'm going to call it x. So I'm going to say, well, let's modify this and say this is x squared dm. Now what does this mean now? I've got to change dm in terms of x. So how do I do that? Well, think of, let's blow this guy up. Here's my little dm here. It has a length of dx, doesn't it? Okay, so what I want to do is I want to get dm in terms of dx. Well, anytime you have a line like this, use a linear mass density. And we talked about this before when we did center of mass. But let lambda is the variable we use to represent a linear mass density. And that mass density, since it's a uniform rod, is the total length. The total mass divided by the length. So it's the length per unit mass. The mass per unit length, m over L. So dm, the mass of this guy, is going to be equal to m over L, that is the total mass per unit length times my little tiny piece of length, dx. Okay, so I've done it. I have successfully changed dm to dx, but I have to multiply it by the linear mass density. So I substitute this in here, and so I now get I is equal to the integral of x squared times dm, which is now m over L dx. I now have to think about where I'm going to integrate, from where to where. Now we're in terms of x. So where am I going to start integrating, and where am I going to end integrating? Well, let's start over here and integrate, and stop here. Well, what is my position of x right here? In terms of the variables I know. It's negative. It's on the negative side of x. That's good. 1/2 L, or L over 2. And so that's where I start on the x, and then where do I finish? L over 2. Positive L over 2. Now this is an integral you can all do. Okay, so this is going to be equal to, well, bring the m over L out. And then we have x squared times dx. That's x cubed, right? But you got to divide it by 3. And then you have to evaluate it from negative L over 2 to L over 2. And so now I've got to go through all this, and it looks pretty bad. It's m over L. Let's put the 3 over here. And then we'll put in brackets our valuation here. This is going to be L over 2 cubed, which is what? L cubed over 8. Is that right? Minus, now what is negative L over 2 cubed? Negative L cubed over 8. And so this is m over 3L. Now what is L cubed minus negative L cubed all over 8? So this is times 2L cubed over 8. So this becomes a 4. This cancels, that becomes a square. And we get our answer. I is equal to, well, 3 times 4 is 12. So we have 1/12 ml squared. And that's my answer. Okay? Now, here's something I want you to see, and let me zoom out on the camera so we can see both of these problems. Now, this is my rotational inertia for a stick where I'm twisting it around the center. And this is for a hoop. But notice something. When you reduce it all down, you have mass times a dimension squared. A length of some kind squared. A mass times a length of some kind squared. Out here is a 1. Out here is a 1/12. Why 1/12? Because look at a lot of the mass of this stick is really close to the axis of rotation, which makes it very easy to twist. It has very low angular mass compared to a hoop. In a hoop, all of the mass is as far away as possible. But in a stick, a lot of the mass is really close. So this is going to have, so it's always going to be a mass times the dimension of length squared. It's usually L squared or R squared if it's a cylinder or something like that. And then it's going to be some fraction. Okay? So what you're going to do in the homework then is go through the examples 10.7, which gives you for a cylinder. I'm not going to take the time to do that right now, but if you look on page 304, on page, you have table 10.2, and they've done a lot of the work for you. Here, I'll put it on the camera here. Let me tilt it. And so here are all the different shapes with their moments of inertia. And for, about the centers. So they've done all the calculus for you. You don't have to memorize these or even put them on your equation list. On a test, I would give you these equations, like for a cylinder or, But I do want you to know that somebody did the calculus to figure all these formulas out for the rotational inertia about the center of mass for all these objects. Except for this one. This one's not about the center of mass, and we're going to talk about that next.